So we go back to this. We have another 20 minutes. I hope we can do this. This one is another data path. So write a Verilog code to model this one. So this you can do this based on the example I have shown to you. So maybe you can do this as your homework. And I want to do this one, which is more challenging. All right. So for example, a digital system is modeled by the RTL code below. So in here, we don't have the uh, DU or CU, but we have the RTL code. All right. Assume that signal P and Q are never one simultaneously, means that uh, we have signal P and Q. All right, and P and Q cannot be one simultaneously, or cannot be one at the same time, and the register of positive edge triggered and are initially initialized with data, means that the data is already in the register, not from the outside. You are to use an ALU with the function shown given in the table Q 5.2. So this is the ALU, and yes, y star means that complement y, or not y, y bar. All right, so the ALU, if 0 0 f1 f0 is 0 0, we have add operation. If 0 1, we have sub operation. If 1 0, we have complement the y, and here we have pass y if 1 1. And this is the RTL code. So we can see that in S0 we have two operations, but this operation is depend on one signal, which is P, which is P. So if P equal to 1, so we will do this operation, means that we transfer the content of register B into register A. All right, but if P equal to 0, we do this, where we transfer the complement of B, all right, complement of B to register A. Same as 1, we have two operations also. If P equal to 1, we transfer 0 or make A 0 to uh, uh, we transfer 0 to register A or clear register A. And if P bar Q, not P and Q, is true, all right, we will do this. We complement A and store at A. For S2, if P equal to 1, we, what happened? Okay, in S2, when P equal to 1, so we transfer to A to register B. And if Q equal to 1, we do this, A minus B, and the result is stored in register B. All right, and S2 also, we have another signal. We need to generate the signal. Done equal to 1 means that the operation is finished. So we need to generate a done signal. All right, this is actually an important signal in digital design. When we finish any operation, we need to generate the done signal. All right, because this module, this circuit will be connected to other module as well, will communicate with other module. So if the operation is finished, so we need to tell other module that the operation is finished. All right, because sometimes other module will wait for the result from this module, and this will tell other module to read the result from this. All right, and also in S2, after that you go back to S0. All right, so we have only this, and what we should do uh, based on this question. So from RTL code, derive the FBD, functional block diagram of the data path unit DU, hence write the variable code describing the DU. So we need to derive our own data path unit in this example or in this question. Before that, you are given the data path. This one is given, but this one is not given, but you have this. You have this. So how to answer this question, right? So we need to understand this, the RTL code. All right. So to do that, maybe we can have this, yeah. I need this. So we can try to answer this together, right? Where we will need this thing, and okay, so let's do this. Okay, so to draw the functional block diagram of the DU, so we need to look at what we have here in the RTL code. So in this RTL code, we have how many register? At least, so we have two register, A and B. All right, and we have one ALU. Okay, so we can draw two register. And one ALU. All right. So this ALU, we have X and Y input, X, Y, and we have output here. This is output. And we have the control signal, which is F1, F2. And this is register A and this is register B. Okay. So we will look at the connection for this operation. So this operation will define the connection of our data path. Okay. So let's look at this operation. So we want to transfer B to A. Means that from B need to go through this register, this ALU, and then go to A. All right. So we can have something like this because we can pass B to A through this operation, right? Pass Y means that B, we need to connect to Y, and then we pass using 1 1 here, 1 1 as F1, F2. We pass B to this and we send to A, right? So we can have something like this. From B, we can go through this and use this 1 1, 1 1, and we go to A. And for the second operation, B naught, and we also store at A. All right, B naught, B bar, and store at A. So we can use this one also because we can have the complement Y here. All right, just select this to 1 0 and we can have not B and send it to A. So we can use the same connection here, right? Should be no problem with this connection. But now let's look at S1. S1 we have pass 0 to A, all right? Pass 0 to A or transfer 0 to A. So this one is a little bit tricky, all right? So we can uh, move 0 to this, but we not here not don't have any input from outside, so we can actually change this to something like this because we have this ALU, right? So we can have something like this. We can change that to A minus A so that we can have A is 0, right? A minus A for this. So change this to A minus A, and how to get A minus A? So means that in this ALU, we need to select 0, 1 here, 0, 1, so that we have the sub operation x minus y, but we need to have A here and A here. But this, something like this, A here, and we need to A to be there also. But this one, you have B already, it means that you have two input now to enter one input here. All right, means that you need a multiplexer here. So uh, instead of this, so you will need a multiplexer. So the multiplexer, all right, you need a multiplexer here so that you can implement A minus A. So see, this is A, and you have we name is this as Y select. All right, so this is 0, this is 1, for example. All right, so if we set Y select equal to 0, means that the input for Y is A, this is A, and X is A. All right, and we select 0, 1 here, means that X minus Y means that A minus A, and we can save in A. So this should be the circuit for this operation. And for the second one, for S1, A inverted, A naught, all right, A naught is transferred to A. So A naught is transferred to A. So how to get A naught? So we send A to this one because only Y we have complement, right? X we don't have complement X for this function. So we send A to this, and using this complement Y, which is 1 0 here, 1 0, 1 0, so that the data will flow this way, and you have A bar here, and you send to A, all right, here for this one. Okay, so we can use, no need other connection, we can use this connection, no problem. For the next one, which is S2 to A, and we store 2A in B. So how to get 2A? So because we have the plus here, yeah, the plus operation, which is 0 0 0 0, when we use 0 0, which is plus operation. So to get 2A, we can change this to this. All right, so that we get 2a. Okay, so to get 2a means that we have a here, should be no problem because this is directly connected from this. And to get a here, you just select y select set to 0. So you have a here and you can have 2a here. And send to b. Now you want to send to b. So you need another connection, which is from the ALU into B. So you can share the bus, should be no problem, right? And this line to A is sent to B, all right? Here, for this, should be no problem. And next one is A minus B and store at B. So whether we need a new connection or just use the this connection can be done or not. Yeah, the last operation. So we want to do A minus B again. Here A minus B. So of course we need to select the minus operation, which is 0, 1 here. Right? So how to get A minus B? So this is A, of course, this is A minus B. So you set Y select to 1. Yeah. Y select to 1. Then you can have A minus B here. All right. This is A minus B. And this can be go to B. All right. And for done, this is the signal generated by the CU, not DU. Okay. So meaning that this data path unit can be used to implement all of this operation already, because to transfer from B to A we can do this. B, Y select equal to 1, go to this and select pass Y, which is 1 1 here, 1 1, and we can send to A. For this one, complement B, again Y select equal to 1, and we select complement B, which is complement Y, in this case 1 0 here, 1 0 here. So we have complement B here and we can send to A, right? Send 0 to A, again 0 to A, we see we will do this. Okay, A minus A, so A here, select Y select equal to 0. So we have A here and A here, and we select minus, which is 0 1. So we have A minus A here, or 0, and we can send back to A. So should be done this one to A. For this one, to A, so we know that to A we can implement using A plus A. Okay, again, this Y select equal to 0, so that we select A here, so A and select plus, which is 0 0, so that we have plus A here, and we send to B. Should be no problem for this one. And for this one, A minus B, easy, because we have this A. How to get B? Select this to 1, so you get B here, minus 0 1, so you set 0 1 here, you get minus, so you have A minus B here, and just send to B. All right, so meaning that this data path unit can be used to implement all these functions, all these operations, right? So this is the answer for the for the equation A. All right, and of course you need to write the Verilog code for this. So try to go back and write this the Verilog code for this to describe this circuit, which is very easy. Now look at the second question. Derive the RTLCS table applying the control vector format LDA, LDB, F1, F0, Y select. Okay, done. All right. So actually this question give you the hint already. What is the signal that you have? Y select. This is actually this Y select. All right. You need to have a multiplexer for this. Done. So we want to create the RTLCS table for that. So we can do that by having this. Okay, let's create the table. So we have this table, and maybe we simplify the table a little bit so that we can have it all. This is our so we need to have this. This is RTL code, and this is the control vector where we have we call it CV. We have what is the name that we want here? LDA, LDB, F. All right. So we have LDA, LDB, F1, F0, Y select, and done. All right. Any other signal? No. So based on this, right? So we have this LDA, LDB, F1, F0, Y select, done. Okay, and is this based on this RTL code, yeah, this RTL code, and also the our this. All right, so let's do this. So for the S0, maybe we can use this S0. We have P, and we transfer B to A. So how to transfer B to A? All right, the first operation, we want to transfer the content of B into A. So here, the content of B, so we need to make B available here. So of course, Y select, we need to set this Y select to 1 so that B can go to this, yeah. And the operation here, because we want to pass B from this to this, so pass B means that we pass Y here, so this one should be 1, 1. And if B is available on this wire, this bus, all right, means that it's available here. And to load B into A, so LDA must be equal to 1 here, right? So LDA must be equal to 1. This one should be equal to 1, 1 based on this. Y select should be equal to 1. And the operation is not finished yet, so should be equal to 0 for done. And LDB should be equal to 0. In this case, we don't want to load any data into B, right? So that is for B transfer to A. What if we want to transfer for this operation, right? B bar or complement B into A. Okay, so for this one should be the same, right? Because we want B, but here we want B, yeah. Here we want B bar. So the operation here should be complement Y because B is at Y. So to complement Y, we need to select F1, F2 to 1, 0. Okay. So, and we want to load to A. So LDA must be equal to 1, just like this. So for the second operation, if P LDA must be equal to 1, LDB still 0, but this one should be 1, 0, and Y select should be still 1, and this one should be 0, right? So that is the second one. The next one, okay, so S1, P, A, actually A minus A, right? A minus A in this case to have 0. So how to do that? Again, we need to look at this. And we want to save in A. So first thing is that LDA must be equal to 1. And to do A minus A, here we need to have A, and here we need to have A, and this operation is minus. So to have operation minus is this, yeah, 0, 1. So this should be 0, 1. And this one will be X. X will be always A because there is no other option. So this is A definitely. But to get A at Y, so we need to select, have Y select equal to 0 so that we have this. All right. So the others should be same. So LDA should be equal to 1. LDB still 0. F1, F2 should be 0, 1. Y select now should be equal to 0, and done is not done yet, so it should be equal to 0, right? So that is for this operation. For this operation, the next one is when P bar Q, so we should do A is A complement, all right? So how to get A complement and store the result in A? So again, we need to go back here, all right, and look at this. Of course, we want to store the result in A, so LD1 must be 1. And if we want to complement A, all right, so because complement is only available at Y, yeah, so we need to select 1, 0 here, 1, 0 for complement, all right. And to make A available at Y means that Y select should be equal to 0, so that we have A complement here because we select 1, 0 here. All right. So that is the signal that we need. So again, LDA should be equal to 0, 1. LDB should be equal to 0, but this one should be 1, 0, 1, 0, and Y select should be 0, and done still 0. All right. And the last one, last state, S2. Let's use this S2. So the first operation will be if P equal to 1, what we do is P is loaded with 2A, and 2A we know that we change to A plus A. All right. So to have this, again, we need to go back to this. And what we want is to store in B, right? To store in B. Okay, to store in B means that LDB must be equal to 1 in this case. And we want to have A available here and A available here, and we select plus operation. So plus operation must be 0, 0, 0, 0. And we want to have A available here, so Y select should be equal to 0. Okay, that's it. So in this case, LDA equal to 0, LDB now equal to 1, and the operation is 0, 0. Y select should be equal to 0. And now in this state, done should be equal to 1. Means that finish, done equal to 1. Right? Now the last operation will be this Q A minus B. All right. So the last one we want store at B, and the operation is A minus B. So again, we need to go back here. Right? We want to do A minus B means that we want, and store at B means that this must be 1, and we want to have A here, B here. All right, and A is yes always available here. Yeah. To have B here, Y select should be equal to 1. That's, we have B here, and this is minus operation should be 0, 1. Right? So that is the signal. So this is should be 0, 1, and this is 0, 1. Y select should be equal to 1, and done should be equal to 1 also, because we are at state S2 equal to 1. All right. So this is the RTLCS table. All right, that answer number question B. Right. So this is should be the this should be answer for B. Yeah. Okay, so B is done. So we have another one, which is C. Now C is interesting. Consider the situation if in state S2, the control sequence signal P and Q are allowed to be 1 simultaneously. What will be the problem? And suggest how would you overcome this problem? All right. So in the question before this, it is said to that P and Q are never 1 simultaneously. But if we allow that to happen, P equal to 1 simultaneously, what will be happen? What will be the problem? All right. So the problem is that when you look at this state, yeah, we have two operations actually, and these two operations will write data into B, into the same register, all right, which is B here. So but we say that P and Q will never 1 simultaneously, means that at one time, right, at one time only one operation is allowed. Yeah, because if P equal to 1, Q should be equal to 0, means that this is not going to be implemented. All right, if P equal to 1. So B will receive this data only. And if P equal to 0 and Q equal to 1, B will receive this data. All right. So we don't have any problem if P and Q is not set to 1 at the same time. All right. But if P and Q is set to 1 at the same time, means that you try to write two different data into the same register. So what will happen? Means that your data will be corrupted, will be invalid, right? Because you don't know exactly which one is go to be. So depend on the speed, right? If this one go first and this one go before after that, all right, means that the data in B should be this one. But if this one perform first, this one, and this one is the next, so the data will be this one. So we don't know exactly which one will go first or go later, because this should happen at the same time. All right, so this is cannot be done, yeah, cannot be done. All right, when P and Q equal to 1 at the same time. So that is the problem. All right, that is the problem. Now how to avoid that? Yeah, suggest how to overcome this problem, how to avoid that. So any idea? So the best way to avoid that is that you separate these two operations into a new state, yeah, S3. Means that you have only one operation in one state. Then should be no problem, because if now you have something like this, okay, from this, so you have S2 is now for 1, and you have another state. Okay, so you can see that when we do this, yeah, in S2, for example, if P and Q equal to 1 at the same time, all right, what happened is the system will always do this, okay, because at S2, all right, in this state, we never look at Q, all right, we only look at P, all right. So doesn't matter Q equal to 1 or 0, this will not going to happen as S2, all right. Same as S3. When we do this, when Q equal to 1, we will do this. P, we don't care. Whether P equal to 0 or 1, this thing will not happen because we are in S3. All right, so that is uh, the uh, the way to solve that problem. Yeah. So any question before we end this class session? All right. Any question? So if no question, we will end the class here. And next week we will look at chapter 6, all right, where we will use what we have learned in this chapter, all right, to build a digital circuit or the even more complicated the circuit, where will have the or we will start the design from the algorithm. All right, we will start with algorithm, and from the algorithm we will design the circuit using RTL design methodology, and we also will measure the performance of our circuit. We will look at the speed of our circuit. We will look at the power consumption of the circuit, and so on and so forth, and the size of the circuit as well, right? That we call the all of this we call the performance metrics of the design. Yeah. Okay. So if no question, so we will stop the class here. See you next week. Thank you.